electromagnetic induction. We have already studied that if we keep an electric conductor in a magnetic field such that the direction of the current flowing through the conductor is perpendicular to the magnetic field, then a force is exerted on the conductor. Due to this, the conductor moves. But what will happen if an electric conductor is moving in a magnetic field or the magnetic field around the stationary conductor is changing? In order to find out an answer to this question, research was done by the great scientist Michael Faraday. In the year 1831, Faraday showed that an electric current can be produced in a conductor with the help of a moving magnet. Come, let us know something more about this great scientist. Introduction to Scientist. Michael Faraday was an experimental scientist. He was not formally educated. Teenager Michael started working in a bookbinding shop. While reading books there, he got interested in science. Sir Humphrey Davy appointed him as a laboratory assistant in the Royal Institute, London. There he discovered the laws of electromagnetic induction and the laws of electrolysis. Several universities offered him honorary degree, but Faraday refused to accept such honors. Before proceeding further to learn more about electromagnetic induction, let us study about an current detecting and measuring instrument. Galvanometer. Galvanometer is a sensitive device used to detect the presence of the current. It works on the principle that the current-carrying conductor in a magnetic field experiences a force. Some electrical measurements can be done using the galvanometer. A coil is positioned between the pole pieces of a magnet in such a way that the pointer on the galvanometer dial is connected to it. When a small current, as that of 1 milliampere, flows through the coil will rotate. The rotation will be proportional to the current. Voltmeter and ammeter also work on the same principle. In galvanometer, the pointer deflects on both the sides of the zero mark depending on the direction of the current. After understanding about galvanometer, let us now do some activities to study about the electromagnetic induction. Activity. Let us first take a long copper wire, a bar magnet, and a galvanometer. Now we shall keep two stands at some distance from each other and fix each end of the copper wire with each stand. Let us consider this position of the copper wire as position A. Connect one wire from one end of the copper wire and connect it to the positive terminal of the galvanometer. Let us connect other end of the copper wire to the negative terminal of the galvanometer. Keep the bar magnet erect in such a way that one of its poles is below the copper wire. Let us now shift one of the stand away from the magnet so that the wire becomes taut. Let us consider this position as B. Observe the galvanometer. What do you see? We see that the pointer in the galvanometer gets deflected and quickly comes back to zero. Now shift the stand near the magnet so that the wire again comes to position A. Now observe the galvanometer. The galvanometer again shows a quick deflection, but this time it is in the opposite direction. If we keep on moving the wire from A to B, the pointer in the galvanometer gets deflected. This is called Faraday's electromagnetic induction. Let us now keep the wire fixed. We shall now move the magnet away from the wire. On observing the pointer in the galvanometer, we see that the pointer in the galvanometer shows deflection to one side of the zero mark. Now we shall again move the magnet towards the wire and observe the pointer in the galvanometer. This time the galvanometer pointer shows deflection in the opposite direction. Thus, from this activity, we understand that if a conducting wire is kept moving in a magnetic field, a current is produced in it. Also, current is produced if the magnet is moved around the fixed wire. Come, let us now do another activity. Activity. Let us first take one rectangular loop and one solenoid coil. Now connect the solenoid coil to a battery through a plug key. Keep the plug key open. Let us connect the rectangular loop to the galvanometer. Now close the plug key and observe the galvanometer. The galvanometer shows a quick deflection on one side and again comes back to zero. Why does this happen? The current flowing in the solenoid coil produces a magnetic field around the rectangular loop. Now keep the plug key open. What do we notice? We will notice a quick deflection on the other side of zero mark and the pointer again coming back to zero. Let us now close the plug key and let the current flow through the solenoid coil. Displace the solenoid coil laterally with respect to the rectangular loop. Observe the galvanometer. We see that the pointer in the galvanometer deflects quickly and comes back to zero. This means the current is still produced in the rectangular loop. Now we shall move the solenoid coil longitudinally, that is, first towards the loop. Do we see any deflection in the galvanometer? Yes. Pointer of the galvanometer shows a quick deflection and comes back to zero. Let us now move the solenoid coil away from the loop and observe the galvanometer. There is a quick deflection in the galvanometer on the other side of the zero mark. If we keep on moving the solenoid towards and away from the loop at a faster rate, we observe that faster is the displacement of the solenoid, larger is the deflection of the pointer of the galvanometer. Thus, we can infer that whenever electric current in one coil starts or stops, then an electric current is produced in the nearby coil. Let us now change the amount of current flowing through the solenoid coil by keeping the solenoid coil stationary. We shall connect the rheostat in series with the battery. Let us now change the current passing through the solenoid coil and observe the galvanometer. What do we see? We see a quick deflection in the galvanometer and the pointer returns to zero. This indicates that even if the solenoid coil is kept stationary, a change in current in the solenoid coil produces a current in the loop. After a series of activities based on electromagnetic induction, now it's time to study Faraday's Law of Induction. Faraday's Law of Induction. If a current is switched on or off in the solenoid coil, a current is induced in the coil. Such induction is also observed when the current in the solenoid coil is increased or decreased. Current is induced in the coil when it is moved aside from the front of the solenoid. From all these experiments that we have performed, it is understood that whenever the number of magnetic lines of force passing through the coil changes, current is induced in the coil. This is known as Faraday's Law of Induction. The current produced in the coil is called the induced current. We have seen that the current is induced in a conductor kept in a magnetic field. But when will the induced current in the electrical conductor be maximum? It will be maximum when the direction of the motion of the electric conductor is perpendicular to the magnetic field. Come, let us now understand How to find out the direction of induced current? Fleming's right-hand rule. In order to show the direction of the induced current, Fleming's right-hand rule is very useful. According to Fleming's right-hand rule, stretch the thumb, the index finger, and the middle finger of your right hand in such a way that they will be perpendicular to each other. In this position, the thumb indicates the direction of the motion of the conductor, the index finger points in the direction of the magnetic field, and the middle finger shows the direction of the induced current.